So if you're a neural networks student or professional, of course you already know that John Hopfield and Geoffrey Hinton received the 2024 Nobel Prize in Physics. And are you in a position to explain what that means? Suppose you're in the elevator with your boss and he or she asks you, or you're doing a job interview and over lunch the tech recruiter very sort of casually says, what do you think about that word and how do you understand that to play out? Well, most of us don't have an easy answer because it involves referencing the Boltzmann machine, the first generative neural network, against the originating statistical mechanics equation, specifically the Ising equation. But I think today we can get a little tiny insight into a portion of this, not the whole thing all at once, but a lead into some significant little element that will set you apart from most of the other professionals. So let's dive in. First, if we haven't met before, I'm Dr. Aliana Marin, founder and chief scientist with Themesis Incorporated, founder of the Themesis Academy, and professor in the top 10 terms in Statistical Mechanics 3-week short course being offered by Themesis. So in this short course, week 1 is general thermodynamics, week 2 is the actual statistical mechanics. Yesterday on day 9 we had entropy, and now we're going to address something called the partition function. Not completely, we're not really doing equations today. This is sort of like a light, I won't say fluffy, but intuitive feeling, getting a gestalt sense of how the partition function works. And we're going to relate it a little bit to the Boltzmann machine. And by the way, we developed that connection further in the remaining days of week 2 and in the early part of week 3. So here we are, the Boltzmann machine, whether just it alone, and by the way, I do mean the restricted Boltzmann machine, the one where the visible nodes connect to the hidden nodes and vice versa, but not within the same set. And what we're going to talk about here pertains to whether or not it's a single Boltzmann machine or a tier of them in one of those deep architectures. So if you've perchance looked at one of the classic papers, for example, Salakutinoff and Hinton, 2012, where they describe the deep architecture in a little bit of detail. And first paragraph alone is so difficult to read. Earlier in the short course, like week 1, I did a full 10-minute tutorial just on paragraph 1. And there's a lot of terminology in there. And if you read the paper, you'll see the Ising equation. They don't call it that, but that's what it is. And it connects beautifully and directly to the architecture. That part is so elegant, so pure, so easy to visualize and understand. But you know what? They don't mention entropy. They make some assumptions, among them that you already know the Ising equation and that you understand that entropy is expressed in the data distribution. So it's a little up to us to fill in the gaps. So we make the connection as we read. So we have to say, here's the enthalpy part. That's where you find the Ising equation. That's where you find the connection to the architecture. And they don't say, here's the entropy. In fact, entropy is noticeable by its absence, especially since you're seeing all these other terms. So you might very realistically look at this and say, what gives? What happened to the other half of that free energy equation? Where's the entropy? And the answer is this. They hide it. They assume that you already know your stat mech. They assume that you understand the breakdown. They're treating entropy as though it's the water in which you swim. The whole free energy equation is something so known to everybody that they don't need to explain it. They just jump into particulars. Indulge me for just a moment while we take a look at a couple of terms from that very famous Salakutinoff and Hinton 2012 paper. And our goal is not to work through the detailed math. That would be an entirely different discussion, a different day. We're just going to identify some key terms because the whole point of the course, the top 10 terms in statistical mechanics, is to provide sufficient working vocabulary so that when we come across these terms, when we're reading the paper, we can identify them. We know where they come from, in particular the ones relating to stat mech, because usually we can figure out the probability-related ones on our own. So let's just have a quick look. This is from section 2 of Salakutinoff and Hinton 2012. The first term, the probability of a vector v with parameter set theta, is shown as an exponential function of a negative energy, and that's the Boltzmann distribution. We mentioned that briefly in the day 9 video on entropy, and then they show that normalizing term, the partition function, where we classically use the term z. And it's z of theta, that would be a partition function associated with a given parameter set. And yes, they do discuss entropy, but typically in a sense that's more related to how do we acquire the data, and specifically, how do we get a good data distribution. So they'll use terms like Markov chain Monte Carlo methods, and specifically, they address things like Gibbs sampling, Markov chains, things that implement the entropy by the data collection. We're not going to go there today. That's one step removed from where we can be. What we've accomplished today so far is to illustrate how the notion of a partition function, which is a normalizing term, shows up in the neural networks literature, particularly in the foundational work for generative AI. Now we'll pursue this more in future vids. Now we're going to close this video for today and pick up with this theme in a different vid. But if you're interested in learning more about how these terms, the top 10 terms in statistical mechanics, are used and understood, especially in the context of neural networks, especially as they pertain to generative AI, do visit Themesis at themesis.com. Go to the Academy page, find a link to our short course, Top 10 Terms in Statistical Mechanics, or go directly to themesis.thinkific.com. This is Aliana Moren from Themesis. Thank you for joining us. Have a lovely day, and we'll see you again soon.